Right, section 11.6 is about absolute convergence, and also two more tests to see whether a series converge, the ratio test and the root test. This video will cover the idea behind absolute convergence and some facts about it. You should read the section to learn about the ratio and root test, and we'll talk more about them in class. So, up to this point, when we've been looking at a series and trying to determine if it converges or diverges, everything we've done has required, well, most things we've done have required that the terms all are positive. Right? In that case, you can use the integral test or the comparison test or the limit comparison test with a known series. On the other hand, if the terms alternate sign, positive, negative, you might be able to use the alternating series test. But there are lots of series where they're not all positive, but they're not this nice pattern alternating either. For example, what if you had a series where the signs went positive, negative, negative, positive, negative, negative, positive, negative, negative? That's not an alternating series, but it's not all positive. So at this point, we don't have anything that will help us figure out whether that kind of series converges. Or any other pattern of signs. Or maybe the signs kind of are a random distribution of positive and negative, so there's no pattern at all. So the first thing we're going to do is just sort of force them all to be positive. Look at the series you would get if you took the absolute value of every term. This is a positive series, so then you can use all the positive series stuff to tell whether it converges. You could use the integral test, or the comparison test, or the limit comparison test, or maybe it's a geometric series, or maybe it's a p-series. So sometimes you can tell whether this series, this related one, converges or not. Right? This series of absolute values. So we're going to have a definition. If the series of the absolute values of the terms converges, then the original series is called an absolutely convergent series. Absolutely because of the absolute values, right? I just want to point out that if your series was already all positive, absolute values don't change that. So any positive series that's convergent is also going to be absolutely convergent. But the real question is what happens if your series is not all positive to start off with. You make it all positive by taking absolute values, then that series converges, then you call the original one absolutely convergent. So for example, the series sine of n over n squared, right? So in the numerator, n is like an angle, and it's in radians, and it's an integer, so it's nothing nice. So sine of it might be positive or negative. It's somewhere in between 1 and negative 1, and it's going to kind of bounce around almost randomly in that interval. So this is not all positive. It's also not alternating positive, negative, positive, negative. But if you take the absolute value of those terms, the absolute value of sine of n over n squared, well, n squared is always positive, so you just really need to take the absolute value of the numerator. And that numerator is smaller than or equal to 1, right? Because sine of anything is between 1 and negative 1, so its absolute value is less than 1. So the terms of the absolute value series are all less than or equal to 1 over n squared. Since the 1 over n squared series converges, it's a p-series with p equals 2, and we have something smaller, the comparison test tells us that this series of absolute values also converges, right? So I forgot that I was dealing with sine of n over n squared. Instead, I'm going to deal only with the series absolute value of sine of n over n squared. It is smaller than a convergent p-series, and it is positive, therefore the comparison test tells me it converges. So this series of absolute values converges. When the series of absolute values converges, that means the original series is absolutely convergent, or sometimes you would say this series converges absolutely. Okay, so we have a series that converges absolutely. That's great and all, but it still doesn't tell us if the original series converges or not. It converges absolutely, but that tells us that this absolute value series converges, not the original. So what does this tell us about whether the original series converges or diverges? Well, there's a theorem that says if your series is absolutely convergent, right, like in the case of this example, right, and remember that means that the series of absolute values converges. If your series is absolutely convergent, then it's also just plain convergent. The original series converges. So in our example, since the absolute value series of sine n over n squared converges, that means that series is absolutely convergent, and therefore it is convergent. This series converges. There are some series where that series converges, but it is not absolutely convergent. So it converges, but the absolute values don't converge. That kind of series is called conditionally convergent. For example, negative 1 to the n minus 1 over n, this is the alternating harmonic series. 1 minus a half plus a third minus a fourth. If you take the absolute value of that, you just get 1 over n, and we know that series diverges. It's a p series with p equal 1. So this series is not absolutely convergent because the absolute value version of it diverges. However, this series does converge because of the alternating series test. It's the alternating harmonic series, so it converges. That means this series converges, but doesn't converge absolutely. Therefore, it is conditionally convergent. Okay, so to sum up, series that are sometimes positive and sometimes negative, you can ask whether the absolute value version of that series converges. And if so, that's called an absolutely convergent series. And if that happens, then the original series, that's sometimes positive and sometimes negative, also has to be convergent. So if you're absolutely convergent, you have to be convergent as well. If you're just convergent, you may or may not be absolutely convergent. And if not, you're called conditionally convergent. All right, so it is important to keep straight that if you know something's absolutely convergent, then you also know it's convergent, but not the other way around. The ratio test and the root test, which we'll talk about in class, are ways to check to see if a series is absolutely convergent. And remember, if so, that will mean that they're also convergent. So we'll see that in class. I also highly recommend that you at least skim that part of the book and look at some examples of the ratio and root tests in action. I will see you in class.